All right, so let's take a look at this one that I posted to Canvas, question 6.39. So if we take a look at the first step that's happening here, right, you see you're going from something where there's no proton on the nitrogen, and now magically we have a proton on there. Well, it's not magic, it's a proton transfer that's occurring. So remember, the tail of your arrow has to start on a pair of electrons. So it's not going to start on the hydrogen. Here, it has to start in the lone pair, and it's going to pick up that hydrogen. But then what happens to those electrons? Well, you can see you end up with a water molecule later on. So the pair of electrons here in this bond are going to end up on the oxygen like that. So now we've protonated the nitrogen. It's got a positive charge because it's got um, uh, 5 valence electrons minus 4 sticks and 0 dots, so it has a charge of +1. And so we would call that a proton transfer. Proton transfer. Now, could anybody tell me how you would categorize this reaction here? Would it be a proton transfer? Would it be a nucleophilic attack? Would it be a loss of leaving group? Or would it be a carbocation rearrangement? Those are our four possibilities. So what about this step here? Could anybody identify that one? Yeah, it's going to be a nucleophilic attack. Thanks, Isaac. Absolutely, right? Why is this a nucleophilic attack? Well, you can see that if you look at this bond here, right, we could draw a resonance form. We're not going to do it, but we could draw a resonance form where we put these electrons on the nitrogen, which would make this a carbocation. And so this carbon, this particular carbon here, is very partially positive, or has a high partial positive charge. So that means it's very electrophilic. And also, you can see there's a dead giveaway that there's a bond between that very same carbon and the oxygen of the water molecule. So how would you make that? Well, the way you would make that is by the water molecule doing a nucleophilic attack, but you can't just draw one arrow because then the bond would have 1, 2, 3, 4, 5 bonds, or the carbon would have 5 bonds. Carbon can never have 5 bonds. And so we're going to have to break this bond and put this pair of electrons on the nitrogen. But there's also a dead giveaway because the pair of electrons is on the nitrogen here. And so this would be a nucleophilic attack. All right, now that we've got that, you can see that the next one, we have the oxygen here has 2 protons on it, and now it only has 1 proton on it. So this must be a proton transfer. Now what's behaving as a base here? Now you can see that we are in acid, right? Because we have hydronium. So that means we're in acid. So the base is not going to be something like hydroxide, right? If you're in a strongly acidic environment, that means that water is going to be the base. And that's good because we have water here, which is going to behave as the base, and water is going to pick up that proton. So you could draw the arrow to this proton. You could draw the arrow to this proton. It doesn't matter. So we'll just draw it to this one over here, and we'll have to put the lone pair back on the oxygen, right? So the oxygen can have 2 lone pairs. All right. Now, what about the next one? Could anybody tell me what kind of mechanism is occurring here? We have the nitrogen. It has 1 hydrogen, and now it's got 2 hydrogens. So how would you classify this one? Would it be a loss of leaving group? Exactly. Thanks, Isaac. It's a proton transfer. Again, right? We're transferring a proton. So proton transfer. And so, right, we're going from the nitrogen with 1 hydrogen to 2 hydrogens, and we have a strong acid here. So the acid is going to protonate. So we start with our curved arrow on our pair of electrons here. We're going to pick up this proton. We're going to put the lone pair back on the oxygen, and there we have it. Now, the next part here, this one might be a little bit tricky for you, but what's happening here is you're going to open up the ring. You can see that the nitrogen ends up over here, but it was part of the ring. So where are we breaking the bond? So look, if we color code this carbon in red, it's this one. And then you can see that you're breaking the bond between the carbon and the nitrogen. So we're breaking this bond here. Okay? So when we break that bond, well, how are we going to break it? You see that the oxygen goes from having a single bond and 2 lone pairs to having a double bond and 1 lone pair. And so we're going to take one of those lone pairs, we're going to make a pi bond, and then we're going to break this bond, and we're going to put this lone pair over here. So we open up the ring that way. Could anybody classify this? It's not a proton transfer, that's for sure, because there's no protons being transferred. Could anybody classify this one? It's not a carbocation being rearranged. I don't see any nucleophiles attacking. Right. Thanks, Rubio. It would be a loss of leaving group. Right. That's exactly what's happening here. Is that this group, the NH2 group, is functioning as a leaving group in this particular case. All right. Cool. So the next one is going to be another proton transfer. We can tell because we're going from this oxonium ion, where you have the protonated oxygen. We call that an oxonium, and then you're losing the proton here. So who's picking up the proton? Well, water, since we're in a strongly acidic environment, water can behave as a base. So it's going to pick up that proton, and we're going to put the lone pair back here. And so if you're astute, and I know you all are, right, you know that there's going to be an equilibrium. If we're in a strongly acidic environment, right, that means that we're going to have water, and we're also going to have its conjugate base, right? There's no such thing as H4, that doesn't exist. So you notice that we keep going back and forth between hydronium, which is a strong acid, right? This is the acid, and this is its conjugate base. So you notice that we have hydronium, water, water, hydronium, right? Water. Those are the acids, or that's the acid and the base that is going to be used over and over. And so if you need a base, it's water. If you need an acid, it's going to be hydronium, because you have both of them in the solution, right? They're both going to be present based on the fact that they're going to be at equilibrium. So there we go. That's that one. This next one is these ones are kind of tricky. So I don't know if, this first one, if you did it, I'll post the solutions to these, but this one is pretty tricky, this one here. But you can see that in this case, the hydroxide is behaving as a base. It's picking up this proton, because you can see that this proton is being removed. So it's like a little cascade of curved arrows, right? We're going to pick up this proton. Then you need to make a double bond. So you're going to take this pair of electrons, make a double bond. Then you need to make a double bond here. So you're going to take this pair of electrons and make a double bond. Then the oxygen, which has a formal charge of 0, right, is going to take on a pair of electrons here, so that it ends up with a negative charge like that. Okay, so you end up with this anion. And then we need to lose nitrogen somehow along the way. And so you can see that when you take and you put 3 lone pairs here, that you're making a methyl ketone, like that. What else is going to happen? You're going to end up breaking this bond here to make a triple bond. You're going to end up making the nitrogen molecule and losing the chlorine like that. So you end up with nitrogen gas, you end up with a chloride ion, and then you end up with this bifunctional compound, which has a ketone and an alkyne in it. Anyhow, I'm going to skip the last one for now. And again, I'll post the solutions to the last one, which is kind of a tricky one. But anyhow, I wanted to take a look at some other practice problems from the textbook, okay? So let's try another one. This is question 6.40. I'm going to assume that some of you have tried this problem already, but it just says draw the curved arrows for each step in the following mechanism. And I also want to add something to that. I want us to identify, are these proton transfers, nucleophilic attacks, loss of leaving group, or carbocation rearrangements. This reaction here is called the formation of an acetal. So this is a functional group that is not covered in this class, but it is covered in organic chemistry too. And this is actually a mechanism that you have to know in organic chemistry too. So kind of getting a jump on the game here. All right, so we're starting out with this ketone. You can see we have this protonated oxygen here, or diprotonated, so that it has a positive charge. So if the oxygen has a positive charge, that's going to behave as our acid, right? Our proton donor. So we're going to pick up this proton, because you see we have an oxonium ion here. And so we're going to draw a curved arrow to one of the protons, and we're going to break that bond. Could anybody identify this mechanism out of the 4? And it's not a trick question or anything. What would that one be? Excuse me. Thanks, Isaac. Absolutely. It's a proton transfer, right? Because we're transferring a proton. Now, the next one's something we haven't seen, I don't think, this morning. So if I look at this oxonium ion, let me test your knowledge based on what we talked about yesterday. Okay, if I look at this protonated ketone here, this carbon that I have highlighted in blue, would you say that carbon is a strong electrophile or a strong nucleophile? That carbon in blue, is that a nucleophile or an electrophile? Yeah, thanks, Isaac. Thanks, Rubio. It's a very powerful electrophile, isn't it? Right? That's a super strong electrophile. That's one of the strongest electrophiles you're ever going to run into, right? Because you could draw a resonance form like this. We're not going to worry about it a whole lot, but you could draw a resonance form like this where you show the positive charge right on the carbon. So yes, that carbon is very strongly electrophilic, okay? So if you're wondering, well, why do we draw this resonance form? Well, we covered that in chapter 2. The reason why is because in this resonance form, everything has a complete octet, whereas in the other resonance form, the carbon doesn't have a complete octet. But you can see that we're forming a bond between this carbon and this oxygen, okay, or one of the oxygens of that dialcohol, that what we call a diol. Anyhow, this is ethylene glycol. It's the alcohol that's found in antifreeze. Anyhow, so what are we going to do here is we're going to take a lone pair and we're going to attack this carbon, but that would give the carbon 5 bonds. We can't have that. So we're going to break this pi bond and put a lone pair of electrons on this oxygen. Could anybody describe this mechanism? Would it be proton transfer, loss of leaving group, nucleophilic attack, rearrangement? Exactly. Thanks. This is a nucleophilic attack. Exactly. So this is the kind of rationale we want to have. Now, in the next step, we're going to do another proton transfer, right? We're starting it with a proton here, and it's gone over here. And so if this was our acid in the first step, that means that this must behave as a base because it's its conjugate base. So the base is going to pick up the proton. So we're going to pick up this not my best curved arrow. The base is going to pick up this proton. We put the lone pair over here. Now, next we need to protonate this alcohol. So we're going to pick up this proton here like that. And now it's protonated. So this would be another proton transfer. This was also a proton transfer. The next one must be the loss of a leaving group. You see the negative sign. When you see the negative sign, it means leaving. It means it's going away, okay? It's gone from the molecule. So how would we do that? Well, you can see that we have to form a double bond between this oxygen and the carbon, okay, the middle carbon. And so we're going to make the double bond, but that would give this carbon 5 bonds. That's impossible, so we have to break this bond like that. Maybe I could squeeze it in better like this. There we go. Anyhow, so we've lost our water molecule. And then what's our next step going to be? You can see that we've got, so this is a loss of leaving group. The next one, we have a very strongly electrophilic carbon, the one that I've highlighted in red. And we have an oxygen from an alcohol, which is a good nucleophile if you put it in the presence of a really strong electrophile. So that's going to act as a nucleophile. So we have a nucleophilic attack. And the last step is going to be a proton transfer to regenerate our acid. So this is going to be our base, pick up the proton, and there you go. So this is a proton transfer. All right. So again, I can't stress it enough that you've got to practice these with a pencil and paper. You can't just watch it and just read it and look at it. You could never learn it that way. It's got to be practiced with a pencil and paper. All right. Let's switch gears for a second and talk about, these are just some questions that I took out of the textbook. All it says is predict whether the following carbocations rearrange, and if so, draw the expected rearrangement using a curved arrow and the resulting carbocation. So let's start with A. So this is just 6.41A from the textbook. We have a secondary carbocation in here. Really nice secondary carbocation. Will this secondary carbocation rearrange? So what are our options? We can either have a hydride shift or a methyl shift, one or the other. Could anybody answer that? Would this one undergo a rearrangement to make something? Could it make something more stable if it rearranged? Yeah, absolutely. It would undergo a methyl shift, right, Isaac? Yes, because if this methyl group moves over here, then we end up with something that looks like this. So now our methyl group is over here. This methyl group is here. And now the positive charge is moved over here. So now we've gone from a secondary to a tertiary carbocation, right? You might be tempted to say, well, what about this neighbor, the neighbor in green? What if I moved this proton over like that? Well, if you did that, okay, what you'd end up with in that case would be this, where you'd have the positive charge here. So you'd go from a secondary to a secondary. So there's no reason for it to do that. So that is not going to happen. It doesn't give you anything any more stabilized. All right, so we get a methyl shift for the first one. So we'll put here methyl shift. What about B? In B, we have a secondary carbocation. Debating that. Would this one undergo a carbocation rearrangement? Is it possible that it would rearrange to give you something more stable? Would that happen in this case? Anybody? Yes. Okay, good. So to review, if you're unsure, here's what you've got to do. You look at the carbon that is the carbocation, okay? Then you look at its neighbors. It's got two neighbors, one here and one here, okay? So on the carbon in red, there's a proton, which isn't drawn, and there's a methyl group. On the carbon in green, there are two methyl groups, okay? If I was to shift over one of the protons on the green carbon, what I would end up with in that case is I would end up with this, where if I just move a proton over, I just shift the carbocation over. So I end up with something that is secondary. And so that is not going to happen because I don't get anything that increases my stability whatsoever. So I'm going to put that over here. But if I look at the red carbon, could anybody tell me, would it be the methyl group or the hydrogen that would undergo the shift? Would it be the methyl group or the hydrogen? It's going to be the hydrogen, isn't it? Yeah, absolutely. Because if the hydrogen shifts, okay, if we move that over, right, Jasmine, then we end up with this, where now we have a tertiary carbocation. So we go from secondary to tertiary like that. If you were to move the methyl group, and I'll just scribble it down here, and I'm going to erase it right after. If you move the methyl group would go, it wouldn't do anything. You end up with the exact same cation, okay? It doesn't change anything whatsoever. And so, yes, that rearrangement is going to happen, but this one is not a methyl shift, it's a hydride shift. I'll just put H shift here. Let's try C. C's a little bit faster. In C, is there any reason for this secondary carbocation to undergo a rearrangement? Would this one undergo a rearrangement at all? No, okay? So we'll just put here, non-applicable, okay? There's no rearrangement here that's going to give you anything more stabilized. D is a little bit interesting because there's a double bond in there. But would this undergo a rearrangement? It's secondary, right? Here's the carbon from the carbocation. This is a neighbor. This is a neighbor. They only have protons on them. So would this undergo a hydride shift? Would it happen in this case? Yeah, in this case, it's not going to happen, is it? Right? It wouldn't happen because if you think about it, if you were to shift over the hydrogen from the red carbon, let's say you took this hydrogen and you shift it over here, then what do you end up with? You end up with this. Oh, sorry, it would happen. My mistake. I was looking at it the wrong way. Yes, it would happen. So this would happen. Why? Could anybody tell me why? Mr. Dion kind of goofed that one up. I should have looked at it closer before class. So yes, this would happen. Could anybody tell me why? What mistake I had made? So we go from something that is secondary to something that is what? This would be classified as secondary allylic. Okay, so since it has a resonance form, right, because you could draw a resonance form like this, it's actually more stable. So you actually end up with something that's more stable in the end. So yes, this would undergo a hydride shift because you end up with something that is more stable. It's resonance stabilized. And then let's try one more, see if I can redeem myself here with this one. So here we have a tertiary carbocation. If you look at the neighbors, the methyl groups, that's not going to give you a hydride shift because that would give you a primary carbocation. So that's a no-no. But if we look at this neighbor here, it's got a methyl group and it has a hydrogen attached to it. Would this undergo a hydride shift or a methyl shift? Would it happen with this one? Like, let's say we shifted the hydrogen. Okay, if we moved the hydrogen over here, what do we end up with? Let me just kind of scribble it down here. So you'd end up with something that looks like this. But now your positive charge is here. So let's try this again. You go from a tertiary carbocation, so let me write this in blue, You go from a tertiary to something that is tertiary, but it is allylic. So it's going to be even more stable. And so, yes, this would happen because the tertiary allylic carbocation has a resonance form, right, that we could scribble down here, which is going to look like this. Like that. So yes, a carbocation rearrangement would occur in this case. All right. So there you go. A little bit of practice on carbocation rearrangement and a little bit of practice on curved arrows, on nucleophilic attack, proton transfer, loss of leaving group, and carbocation rearrangement.